on x and y, right? And that would have been from looking at the ground and looking at the projection of this triangular plane down onto the xy plane, and it would have looked like this. 1, 1, right? And it would have come across like that. And the area of that is 1/2 base times height, so that would have just been 1/2, right? Times -2. So the answer is -2 times 1/2, which is -1. Understand? Whew, 20 minutes. I was going to give you a chance to work one on your own, but I don't think there's enough time. Did I have the homework up there for that section? That's it, right? I didn't put homework. Okay, what you should do for homework for 13.8. How about 13.7? You know the homework for 13.7, right? Okay. For 13.8, you should do like number 3. Maybe 5, 7, hold on. I think 5, 7, and 9 I did. So number 3, 5, 7, 9 is what I have on here. You can also do 11 and 13. All right, there's one last thing I want to show you since I've got 20 minutes, and this will be nice. We will have one day for divergence theorem. It won't take us the whole class, and we can talk a little bit about the final, and we're going to make it to the end of the book. I don't want to start divergence theorem today, though. All right, so here's kind of a cool problem. I found this doing a little bit of research on Stokes' theorem. Let's say that you have a cylinder, okay? And let's say this cylinder has the equation x squared plus y squared equals... Now I'll ask you, do you want it to be a general cylinder, or you want me to actually like fix the radius at something? General. You want to do general? Okay, let's call it... Let's not use r because we might need r. Let's just call it c squared. Is that okay? Some constant square. You want to do a? Okay, I'll do a. Just for you. Yes, that's okay. I'll do that. There you go. A squared. All right, now I have a curve, all right? C, which runs along the boundary of this cylinder. Goes all the way around. Starts here at this point, goes around the back side, comes back, and let's call that C, and let's give it that orientation right there. Got it? I'm not telling you what C is. It's any curve that you can think of that does that. Find the line integral over C of f dot dr. Oh, but I've got to get something real quick. Hold on. Got to get you the vector field. And this has to be done correctly, or else it's not going to work. So give me just a second. Y'all can take a break. You can chat with your neighbors for a minute. Okay, you ready? I'm going to give you the vector field 2xz minus 2y 2xz minus 2y two yz plus 2x x squared plus y squared plus z squared. All right, I'm going to read this out. Someone just make sure I've got this. First component, 2xz minus 2y. Second component, 2yz plus 2x. Third component, x squared plus y squared plus z squared. Okay. All right, so I'm going to put that vector field over here so it's a little easier for me to work over there. 2xz minus 2y, 2yz plus 2x, and x squared plus y squared plus z squared. That's my vector field, all right? That's F. And of course, this we said was x squared plus y squared equals a squared. A is a constant. C is that curve, right? So find the line integral over this, over that curve with that vector field. All right, so what sort of issues or concerns do you have at this point? Do you know what C is? Nobody has given you C, right? Nobody has given you C at all? If you don't know what C is, you can't find a parameterization for it, can you? If you don't know what it is? The best you can do is maybe use Stokes' theorem. But if you use Stokes' theorem, you need to be able to give me the parametric, some way of figuring out what that surface is, right? So you can start working. I'm not saying that the surface in between there, see, the curve is not flat, so you're not going to be able to put a flat sheet right across it. You see that? Understand? So there's a whole lot of things you don't know, right? So this seems like almost an impossible problem at this point, because you don't know the parameterization of C, and you don't know anything about the surface between them. All right, so before I continue with this, I just want to show you on the side here a different surface, but it's going to be very similar to that. Let's say we have a cylinder that looks like this. Oh, that's supposed to be straight. Okay, so this we cut the cylinder, right? And this edge is, wobbling around. Okay, so that's kind of like the C is over here. Yes? Got me? And there's a bottom edge too, which you can't see there. Y'all got it? If we are to use Stokes' theorem, then Stokes' theorem says that if C goes around the edge of a surface, right, then we can use the theorem. If I cut a cylinder in two pieces, I actually have two curves that would enclose this surface, not just one. It's the curve on top here, C, which I said is going that direction over there. And then this bottom one down here, which I will call C2. All right, is that okay? I didn't call this one C1, but I'll call that C2, just so there's no confusion. So do you see that C together with C2 enclose the surface? But there's a problem, because in order for Stokes' theorem to work, when you're walking along the curve, right, the surface is supposed to be to your left. Do you agree? Now, if I walk along this curve, is the surface to my left? What's the surface? What's the surface? Right? So let me do this. How about, imagine cutting this and opening it up. That might help. If I cut it and open it up like this. All right, let's say These 2 points come together. These 2 points come together, right? So which direction was C2 in? Is it this way, like this? Which direction is C1 in? Or C? Would it be this one? See, look, what I did is I cut it right here. I cut it, and I just laid it open like this. Right? Hold on. This one is, yeah, this direction. C and C2. All right? You with me still? Now, if I'm walking along C, let's say pointing out towards us is where our head is, up here. The surface over here is to my left, right? But if I'm walking over here, the surface is actually on the other side. So what I need to do is reverse the direction. So how does that affect things? Let me show you. I'm going to write it down. After I write it down, maybe you'll see it. Do you agree, according to Stokes' theorem, that the double integral over S of f dot ds should be equal to the two line integrals? One that would be the line integral, let's say C was okay, right? Orientation, right? Because the surface is to my left. Plus this one, but the orientation needs to be backwards, which means if I reverse the direction, I subtract, don't I? So how about instead I write minus this over C2 f dot dr. Are you all with me? These two curves, C and C2, enclose a surface. They enclose this surface in here, which is the cylinder. Therefore, the line integrals along those curves should be equal to the double integral over the surface itself. That's what Stokes' theorem says we can do. I had to change the orientation of this curve because I've got to have the surface on my left side. So negative C2 runs that way, which keeps everything oriented properly. Understand? Now, if you said, well, wait a minute, go to the other side of the page, then it's opposite, then I would agree with you, and then all that happens is this one's minus and this one's plus. Okay. Which one? Yeah, they are both closed, actually, because I cut them and opened them up, but that was just to visualize it. These are closed, right? These are closed? I haven't drawn the one over here yet, but the one I drew and erased, they were both closed curves, right? Okay. Y'all okay with this? How's my time? Got 8 minutes. Should be able to do this, I hope. Okay, this is what I'm going to work with right here. I will admit to you, I know nothing about C, right? So there's not a whole lot I'm going to be able to do here. C2 was any curve that I picked that was below it, right? Or above it. It's just a different curve that also goes around the cylinder. What's a nice choice for C2? How about a perfect circle that runs right through the origin, right through the x, y plane, just like that? What if I choose that to be my C2? Right? That I should know about, because I can find the parametric equations for this, can't I? I can draw this curve. It's in the YZ plane, has a radius of A, right? I should be able to draw that. So I should be able to get some information about this, right? That I should be able to get. This, I don't know, but that's kind of what I wanted to know, right? So the only thing really is, can I figure out something about this? Well, all I can hope for, damn it, is that the curl of f, that should be curl, the curl of f is something nice. That's all I can hope for. So are you ready to do curl of f? All right, help me out with curl of f. Sorry, you see I forgot the curl f there? You can't, Stokes' theorem's curl, not f. All right, so what's the curl of f? Maybe we can do it without actually, if I just put the stuff up here, maybe we can do it quickly. Okay, so what do we get? Partial with respect to y of this, 2y minus 2y, which is 0. Okay, what about, cover this one up? Partial with respect to x, 2x, right? 2x minus 2x, but change the sign. Who cares? 0. All right, and then this last one, 2 minus 2 minus, yeah, so that's going to be what? 2 plus 2 is 4, right? Be careful. It almost looked like 2 minus 2, didn't it? But it was, what, 4 here? Agreed? All right. I'm with you there. I'm with you there. That's the curl. Now, this is the tricky part. I would have to come up with some parametric representation of this surface now, right? Right? Because I'm trying to do this, ds. Only hope I have is if I can turn that into the n, right? The n. And that is not necessarily easy to do. But I'm going to look at, I want to just erase in here, convert that real quick over to this. Curl f dot n dot ds, or times ds. What can you tell me about that the normal vector of any, if you take any point on that cylinder, what can you tell me about the normal vector? I'll try and exaggerate it. Here's the cylinder, right, in the room. Normal vector is on the cylinder, right? Is going to be any one of these. Now, they change as you go around the cylinder. Do you agree? But what do they all have in common? They're all running like this, parallel to the xy plane, aren't they? As I move this thing around, they're all parallel to the xy plane, right? What about the curl of f? Tell me about that vector. It's straight up. And what's the dot product of two vectors that are always like that? 0. Do y'all see that? Yes? That's why it was very important that I pick the right vector field for this to work, okay? This wouldn't work with just an arbitrary vector field. So because this normal vector, when I take the curl of f and I dot it, these two are orthogonal, right? Orthogonal. That means their dot product is 0. And that means the left side is 0. Understand? Okay? So if the left side is 0, then that means that these two on the right side, right, are all that's left. Not that they cancel, they're equal to each other, right? So just move this one to the other side, right? And what you have is that so it's saying the work, basically the work around this curve in this particular vector field is equivalent to the work around this curve. And so now what you would do, because I only have 1 minute, I can't do it, is you would set up this one, because this one we can do, right? RT equals, we're A cosine t, A sine t, 0, right? That's R of t. That draws me that circle, C2. This is C2. And then I need the derivative, right? Because I'm going to do, this is negative A sine t, A cosine t, 0. And then when I plug this in, I have to plug this into the field, right? And then that, and then dot. It turns out to be nice. I'm out of time. But there's a lot of like